All right, welcome everyone. Thanks for joining on this Friday. My name is Dan Rippin. I work with Jen Watson, who has been moderating some of these talks and a couple of days before. Welcome everyone, glad you can join us. If you haven't already, please type your name in the chat just so that we have an idea who's here. And also as we go, please add comments or questions in the chat. One of the things that we're going to do a little bit differently is our speaker, who I'll introduce in just a second, Yael Tauman-Kalai, has requested she'd like to take the questions as we go, which I think is a little bit different than we've been doing it. So I'm going to try to keep up with some of the questions as you ask them in the chat, and maybe help stop Yael and call on you to ask a question as we go. Just everyone be forewarned that we're gonna do it that way. So as we get started, I'm really pleased that that we have Yael Tauman-Kalai here to speak with you today. I think this is going to be a fantastic talk. The title of her talk is "The Magic of Cryptography," and I think this sounds fascinating. The short abstract actually has me extremely curious already. Yael got her BA, her undergraduate degree, from Hebrew University in Jerusalem, and then a master's at the Weizmann Institute, and a PhD at MIT, where she was actually a co-winner of the Sprouse Award, if I'm saying that right, for the best PhD thesis at MIT. Really, really cool. And now she's a researcher at Microsoft Research in New England. We're really lucky to have her today. Yael, thank you for joining us. And why don't you just go ahead and take it away, and we'll be asking you some questions before not too long.
Great. So thank you very much. Thank you for joining us. I see there's a lot of students here, which is lovely. And as I said, I think questions are great. So feel free to ask, and the interaction is good. It will help me not go too fast. And also, since I really don't know your background that well, I know you're high school students. I'm used to talking to more senior people. I think it'd be great if you can help me pace myself to your needs. Okay, so let me get the presentation going. Let's see. Okay, can you see my screen? Okay. So so I'm really excited to use the next hour to try to convince you that cryptography is a beautiful field with a lot of magic going on. And I will try to kind of give you a hint of where this magic is. And I'm going to do this. So there's a lot of magic in cryptography. I'm going to use kind of one lens to show you a little bit about this magic. And it's using the idea of proofs in cryptography. And in particular, most of the talk, I'm going to focus on zero-knowledge proofs. And if I have time towards the end, I'm going to say a few words about kind of the evolution of proofs in computer science in general, which was motivated and started from the field of cryptography. Okay, so let's start. So what is a zero-knowledge proof? So zero-knowledge proofs were introduced in the mid-'80s by Goldwasser, Mikhail, and Rakov. Goldwasser and Mikhail are here at MIT. And so what's the idea? These are proofs that essentially reveal no information beyond the validity of the statement. So if you think about it, it's kind of a magical concept, because usually proofs, of course, they give information. If you want to prove a theorem, in the proof, there are some ideas, how you prove it, and so on. A zero-knowledge proof is the opposite. You read the proof, but you learn nothing about why the statement is true. Okay, so is that possible? And how would we define this kind of thing? And when you think about it, the first thing that maybe comes to mind is actually, there's no way. This kind of idea is impossible. And why is it impossible? Because write the proof, and no matter how you write it, how you try to hide things, at the end of the day, a proof is something that I can verify. So it's the fact that I can verify it, that alone is information. In some sense. In particular, the way I want to define zero knowledge, what does it mean to give no information? The idea is, look, whatever you could have done without the proof, with the proof, you could have also done without the proof. But with the proof, you can go and convince someone. Without the proof, you can't. So the proof itself is information, no matter how obfuscated, quote unquote, it is. So, okay, so impossible. Seems like, you can't really get something that's really zero knowledge or, okay, but so now I want to just stop for a second and say, actually, everything we do in cryptography is impossible. So kind of cryptography is an art of getting around these impossibility results, okay? And kind of even, that's kind of all of cryptography. If you think about it kind of in a very straightforward fashion, you'll very fast run into walls. And so it's all about kind of avoiding these impossibilities. So with that in mind, let me actually, even though I convinced you that zero knowledge proofs are in some sense impossible, let me give you a zero knowledge proof right here, okay? So I want to convince you now that it is possible.
Yeah,
Yes.
okay. Can I just interrupt a second? We have our first question. So Alexander Jang, do you want to unmute and ask your question?
Oh, hey, Professor.
Hi.
Thank you for giving us our presentation. And I was just wondering, so I know that the SHA-2 algorithms play a really fundamental role in cryptography. And I was wondering if it's ever possible to reverse them.
The SHA, you mean?
Correct.
Okay, well, it depends on which SHA. Some are reversible, some are not. But this has nothing to do at this point with zero knowledge proofs, right? You're asking a general question.
Correct.
Yeah. So the answer is complicated. The SHA that are used now are not, we don't know how to invert. But this is nothing to, so try to stick with questions that are, I'm very, very happy to ask any kind of questions at the end, but during the talk, try to stick to questions that are relevant to clarification questions, I should say. Okay, that will help you guys. I don't want you to continue the talk without kind of understanding the material, but I'm happy to ask any kind of, broader questions at the end of the talk.
Okay, thank you.
Sure. Okay, so I tried to convince you, I kind of showed you intuitively that zero knowledge proofs are not possible, but now, despite that, I'm gonna now give you a zero knowledge proof. Okay, even though I said it's impossible. So here is the statement I have. So I don't know if you guys see, there's two pencils here. They may look identical to you, okay? But I want to prove to you that they are different, that I can distinguish between these two pencils. Now, of course, I can try to show you, oh, if you see there's a spot or whatever, this pencil has it, this pencil doesn't. But that won't be zero knowledge because now you learned, you found a spot. So I want to do it in a zero knowledge proof. So at the end of the day, you see these pencils, you won't be able to distinguish between them. The only thing that you are able, that they're distinguishable, that they're not the same. But I'm like a magician. I give you the magic, you can't repeat it. You can't do it on your own. You can't now see where they're different. Okay, so are you ready? This is me with my magic. Here it is. Here are my two pencils. I tell you, this is pencil A. This is pencil B. Okay? Now I'm going to give Alexandra the two pencils. I'm going to turn around. Okay, Alexandra can choose whether to keep this A or this B or to change. Okay, so he kind of orders it however he wants, and then I come back, he gives me the two pencils. Now I'm going to tell him which is A and which is B. Now, if they were identical, I wouldn't be able to, I would probably have, they're the same. So I don't know if when I was when I went, when my back was towards you, whether Alexandra decided to flip them or not. So with probability half, let's say with probability half, I'll fail. On the other hand, if they are distinguishable, I'll distinguish because I'll look and I'll see what's A and what's B. So now if we play this game many, many times, 100 times or K times, then if they're distinguishable, I'll always succeed, and you're like, okay, probably, they're not the same. Because if they were distinguishable, at least one of the probability that I'll always succeed, that I'll always kind of be lucky, and guess whether Alexander flipped or not, each time is half. If we repeat it, let's say 100 times, I'm going to succeed only with probability half times 100. So half to the 100, which is very, very, very small. So now what happened? I convinced you. So if all these 100 repetitions, I was correct, I knew what is A and what is B, then now you're convinced. On the other hand, Alexander, you didn't learn, you don't know why they're different. You really learned nothing. Okay, so now you should be a little kind of surprised, confused, I should say, because I started by telling you it's impossible to have zero knowledge proofs. On the other hand, I just gave you zero knowledge proof. So what happened here? So the reason I succeeded in giving you zero knowledge proof is because in my zero knowledge proof, I changed the model of a proof. So when we come up with, I know you guys are, high schoolers rising, juniors or seniors, and I'm sure you're a very smart group. So I'm sure many of you, started, or some of you at least started this idea of proofs in geometry or whatever is done in high school. And so you know how you write a proof. A proof is like a piece of paper and you write this implies this implies this implies this. On the other hand, the zero knowledge proof I gave you was very different than that, right? It was kind of an interactive process. There's a prover who's me, there's the verifier who's Alexander. I gave him the pencils. Alexander kind of, tossed coins with probability half. So we're talking about Alexander became a randomized verifier that with probability half, he switched, probability half, he didn't switch. And then he sent me back kind of the pencils and I replied, what is it? I changed the model. And this is exactly how they managed to construct knowledge proofs.
Yeah, but before you go on, sorry, we have another question. Srivi Balaji, do you want to ask your question?
Yeah, sure. Thank you. So my question is, based on what you explained as what is a zero knowledge proof, is it basically like proofs by trials? So you would do multiple trials of a certain, or multiple experiments of the same proof in order to prove that the proof works without knowledge?
Great. Okay, that's a great question. And the answer is, okay, depends how you define a trial. But the short answer to your question is probably yes. But let me say the answer a bit more formally, okay? I changed the model. So instead of sticking to the standard way, to the standard definition of proofs, which was considered, in mathematics, starting from ancient Greece, thousands of years ago, now cryptographers in 1985 decided, no, we're changing the model of a proof. And what is a proof now? A proof will consist of a prover and a verifier. Okay, that's not that different. But the difference is that first we allow this proof to be interactive. It's an interactive process. So the prover sends a message, the verifier replies, prover sends a message, the verifier replies. And in this sense, Srivi, yes, it's like there's many trials. You send a message, I reply, you send me a message, I reply. So it's an interactive thing. Moreover, this is very important, we allow the verifier who checks the proof to toss coins. So he has some randomness. When he verifies, it's a randomized process. So in the example of the pencils, with probability half you flip, with probability half you don't flip. If the verifier in that example was deterministic, so he either always flips or always doesn't flip, I can cheat, of course, because even if they're identical, I know this is A, this is B. If I knew if you flipped or didn't, I would know the answer. So the fact that the verifier was randomized and the prover in some sense, didn't know whether he flipped or not, that was essential for the proof, for me for soundness or for convincing you that indeed my statement is true. So in an interactive proof, the verifier tosses coins and there's two, the standard condition, completeness, let me see if you can see, okay, sorry. Okay, oh yeah, can you see my mouse hovering, by the way? Yeah, okay. So the completeness just says, if it's in the language, so if X is in the language just means if the statement is correct, for every, this is a symbol of for every statement that is correct, that is true, I will indeed succeed in convincing you with probability 1. This just says P and V talk. They have the instance, the claim X, and V will output 1, namely he will accept the proof, and this will happen with probability 1. So this just says, yeah, if I know the proof, you will accept that with probability 1. But the important thing is, that's where the model changes, the soundness condition. The soundness condition says, if my statement is not true, okay, so for every X, if I try to convince you that X is in some language or that the theorem is true, but it's not, then for any cheating prover, I'm a cheating prover here, P star, I want to convince you that the pencils are different even though they're not, so the statement is false. For every cheating prover, when he talks to the verifier may actually accept, he may output 1, but with very, very small probability. So whereas in standard proof, if the statement is wrong, there is no accepting proof, period. A verifier, you come up with a proof, it's bogus because the statement is incorrect. So your proof is wrong, and it's not going to verify. It's going to be rejected with probability 1 because there's no randomness. In an interactive proof, because the verifier is randomized, even though the statement is incorrect, there's a small chance that he will accept you anyway, but it's going to be very small. And the number I wrote here is arbitrary because I just wrote a small number, but the point is that this number is not important because what we can do, we can repeat. So even if the number here was half, that's good, like in the pencils, that's good enough because we'll do one proof, and then we'll do another proof, and we'll do another proof until you'll be fairly convinced. So if the number here was half, if a false statement is accepted with probability half, if you repeated k times this proof, then it'll be accepted with probability 2 to the minus k, or half k times. So the exact constant here doesn't matter. Okay, the point is it's small. So let me now recap a little bit. Let me step back and say, okay, the goal was to construct a zero-knowledge proof. Using standard definition of a proof, impossible. To get around this impossibility, they defined the notion of an interactive proof, where the proof now is an interactive process between the prover and the verifier, and the verifier is allowed to toss coins. And we relax the soundness condition to say that if the statement is false, you may be accepted, but it's going to be with very small probability. Okay. And now we can define at least the notion of zero knowledge in a way that makes sense. So how would I define zero knowledge? It just says, essentially, without the formalism, it just says, well, I want to say that when you look at this transcript, which I denote by PV of X, okay, X is the statement, the theorem. So if you look at the transcript here, you'd learn nothing. You could have generated this transcript on your own. It's like when I gave you these two pencils and argued that they're different, Alexander didn't learn anything because he could have simulated this on his own. He could say, okay, here are two pencils, okay, change or not change, and A or B correctly because he knows if it was changed or not. So one can simulate this and can generate. So essentially the definition says that there exists an efficient way, we call it this a simulator. So you can simulate this transcript or generate this transcript on your own without even knowing whether the theorem is true or not. So you don't have a proof for this theorem. You don't know if the theorem is true or not, but you can generate this transcript efficiently without knowing anything. So you didn't learn anything. You could have generated this transcript on your own. And in particular, what it means, and this is interesting, that this transcript is not transferable. So with a classical proof, if you give me a proof, I can publish it. I can give it to other people. If you prove to me that Fermat's last theorem is true, I can go to someone else and they'll go, oh, look, I have a proof. The theorem is true. You can verify it, and I can publish it, and I can. Here, if I give you an interactive proof, you're left with nothing. What is this? The reason you're convinced is because, when I sent you this message, the first message, I didn't know what your next message, is going to be. That's what convinced. The order here was important. But at the end, if you just see a transcript, anybody can come up with that. So at the end of this conversation, you didn't get anything that you can actually give someone. And that's why it's zero knowledge. It's like the proof vanished. That's kind of the magic here. Okay, I convinced you, I give you the proof, but when we're done, it's like it disappeared. Okay, any questions? Okay, one thing I want to point out, and we'll see that actually, is that interestingly, even though you didn't quite see it in my example, and that's because,
Actually, Yael, can I just interrupt? So there's a discussion going on in chat, and let's see, Maxwell Zen, I think you had an insight. I was wondering if you could just share it and maybe see if Yael has any comments on that.
Yeah, sure. I just because I think Aiden wanted another example of a zero knowledge proof, so I kind of made one up. I think from what I understand, if someone says something like it's possible to read someone else's mind, and so you just run a bunch of trials where you actually like guess what someone else is thinking, that would be zero knowledge, because there's no like instruction on how or why that's possible, but like you still know that it's possible because they just did it.
true.
Or
Yeah,
would that be another example?
That can be an example, except that if you say you read my mind, how do we know that it's true? So you can say, oh, I read your mind, and you're now thinking about, the omelet you ate for breakfast. How can anybody verify it? It's not, I mean, there's no, but you're right, it is. You can't think of it this way. It's just usually when we think of when we give zero knowledge proofs, it's about a statement that actually has a standard proof. So in the case, what was on my mind, there's no actual proof of that. You know what I mean? It's not, so when our goal is to construct a zero knowledge proof, and we'll see that in the next slide, our goal or their goal, and actually what they do. Let me skip ahead and tell you the kind of the amazing thing. So let me just say one thing and then I'll skip to that. So one thing I want to point out, it's a small thing, but I just want to make sure I say that, is that to get a zero knowledge proof, it turns out that the prover also needs to be randomized. Okay, it also needs to toss coins. Now, in the example that I gave you here, you didn't see that. I didn't toss coins. I just gave you the pencils. The verifier tossed the coin to decide if to switch or not. I came in and told them left or right, like, is it A or B? But the reason I didn't need coins because it was a kind of a physical example. But if we do it digitally, then the prover will need to toss coins, and I'll explain why in a minute. But before I do so, I want to skip ahead to Maxwell's point and say that here's the theorem, okay? And that's kind of really amazing if you think about it. So the theorem is the following. Take any statement that has a classical proof. So in other words, take your favorite theorem that you have a proof for. Okay, I don't know, some geometric theorem, and here's a proof of that statement. I can take that proof and convert it to a zero knowledge proof. So any classical proof, we know how to convert it to a zero knowledge proof. So anything you want to prove, you can do with zero knowledge. That's really, really amazing. And moreover, I'm going to try to be ambitious and prove to you that this is the case. Okay, so let me try to take you guys, which are, most of you rising juniors and seniors, and try to prove to you that any theorem that has a proof, also I can take this proof and convert it to a zero knowledge proof.
Before you start, I just want to pause for a couple of questions. So
Sure.
Let's see. One was from Mindy Kim. Do you want to just share that?
Oh, yeah. So you were talking about how the interactive proofs were not transferable compared to the normal proofs that you see.
Yes.
And I was just wondering if that was because the proofs or the interactive proofs are unique to the prover and the verifier. Is that why
Yes.
it's not really transferable to others?
Exactly. That's a very good point. So when I prove something, I prove to a specific verifier in the interactive setting. And this verifier, the reason he's convinced is because when I send him my first message, he knows that I don't know his second message. I can predict the future. He didn't toss his coins yet. And because I don't know what his coins are, that's what prohibits me from cheating. Now, if you go to someone else, so that answer is yes, it's because I proved it to you. And I give you my first my first message. You gave me your next message, which is often like a random bit or whatever. And then I give you an answer. But the important thing is the reason this proof is sound, or that I can't cheat, the reason I cannot cheat is because I didn't know ahead of time all your random coins. If I knew your random coins all ahead of time before I started, I could cheat. So now when you want to try to transfer it to someone else, they'll be like, how do I know that you weren't the verifier and the prover? How do I know? Maybe, you tossed coins, you told the cheating prover, which may be yourself, I don't know, and now he can, once he knew ahead of time all your random coins, he could cheat, and now you generate this transcript, which is a cheat, and the theorem is false. So that's why it's not transferable. So short answer to your question, yes, you're completely right. It's not transferable because the proof is for a specific verifier. And that's in contrast to standard proofs.
I see. And so it's just unique based on this response and answer. Okay.
Precisely. Yes.
Thank you.
All right, and then maybe just one more question before you go on, and then I want to let you go on. Daniel Chuang, I think it was a somewhat related question, or did that?
Yeah, it is a related question. It's about the transferability of the transcript. Right now, I might be misunderstanding, but it seems like you're assuming that the verifier has to be like a human party. But what if you use like a computer party with like what if someone programs something where you're the verifier, you do have these two pens, the computer randomizes it, feeds it back to you. And because you can't tamper with the computer and like an established group has already programmed the computer to do something, like those results can be shared to others. Like if the computer can verify your results, then it can share it to a bunch of other people, therefore making your proof kind of transferable. Is that?
Okay, so, what you're right that if a computer, you can say, look, there's some computer who checked my proof. And then the computer tells other people, oh, I checked Yael's proof and I verified it. And then you may be, if you trust the computer, so if you trust the computer that he's not lying, that he indeed, talked to me, I didn't know his random coins ahead of time. And, when I talk to the computer, and then he shows you this transcript, then you're convinced. But for that, you need to trust the computer. You can't, so, the computer can lie. It can be malicious. So it's, and let me say, when these zero knowledge, so the crux to the last slide in my talk, these things are used, okay? Today they're used in blockchain, and it's between computers, it's not the humans are involved. So at the end of the day, yes, the verifier is a computer and the prover is a computer too. But still the fact that, if you do it interactively, then you can to make it, if you can transfer it only if you trust kind of the verifier that he indeed talked. Otherwise, there's no proof of that. Otherwise, it won't be zero knowledge in a sense. Okay, so the next thing I want to do is I want to show you that essentially I want to kind of give, of course I'm not going to give you the entire proof. This is a graduate level class, but I want to give you the gist of it. So you won't really understand, but maybe you'll have some feel of how these proofs work. So, there's one of the most important, or the most famous at least, questions in theoretical computer science or computer science at large is P versus NP question. I don't know if you guys have learned about it, but essentially, there's this language of NP which essentially what it says, NP are all the kind of languages that have a short proof or a proof that's verifiable by an efficient verifier. And what's known that there's these languages that are complete. I don't want to define all of it, but the point I want to make is, in order to prove that every proof can be converted to a zero-knowledge proof, it suffices to consider proofs of specific complete languages. Okay, so in particular, what I'm going to show you today and what was shown in the theorems is that I'm going to show you a zero-knowledge proof for a specific language, or specific theorems, a class of theorems, which are the three colorable graphs. So before I say why that's enough, what are three colorable graphs? So a graph is just nodes, which are denoted usually by V for vertices, and a set of, so these are the nodes or the vertices, these blacks, and edges that connect, two nodes. And such a graph is said to be three colorable if we can color it by three colors. I'm going to call the colors 1, 2, 3. I know these are numbers, but not colors, but let's think of 1, 2, and 3 as colors. So I can color them by colors 1, 2, and 3, such that, so it's three colorable if these coloring has the property that there exists no two adjacent nodes, so there's no two nodes or vertices, the same thing, no two adjacent nodes that have the same color. So for example, this graph is three colorable, and here's the coloring. This is an example. So if you look so they're colored by colors 1, 2, and 3, and every two nodes that are adjacent, that share an edge, they have different colors. Okay, this is, by the way, here's an example. This is not three colorable. This is a graph, it's not three colorable. Because if you color this by 1, this has to have a different color, 2, let's say. This has to have a different color because it's connected to both, let's say 3. And now this has to be 4 because he's connected to all of them. So this is, just as an example, this is a graph that's not three colorable. Now, what is known is that it suffices to prove, it's enough to give a zero-knowledge proof for these kind of statements. For theorems, it's enough to prove that given a graph, that it's three colorable in the zero-knowledge way. And the reason why that's enough, which I'm not going to get into in this talk, but just kind of so you know, is because I can take any statement that has a proof, I can convert this statement into a three colorable graph with a coloring. So we know that in that sense, this kind of theorems are complete. Okay, we can take any theorem that you have with a proof, I can convert the theorem to a graph, to a three colorable graph, and I can convert the proof to a coloring. So now all I need to do is give a zero-knowledge proof for that. And the conversion from the theorem to the graph, anybody can do. It doesn't reveal any information. It's just there's a formal way of taking the theorem, parsing it, and converting it into a graph that doesn't reveal any information. Anybody can do it. You don't need the proof for that theorem to do it. So the point is, and for this, what I said now was, I know, way too fast, but the point I want you to take from this is that to give a zero-knowledge proof for any statement, it suffices to give a zero-knowledge proof for a specific type of statements, which are the three colorable graphs. Okay, why that suffices? Again, it falls from completeness, from kind of the fact that three colorable graphs are what's called NP-complete. That's for a different lecture. Okay, but for now, let's just take that as given. And now, suppose you are convinced or you believe me that to give a zero-knowledge proof for any theorem, for any statement, it suffices to just give zero-knowledge proof for three colorable graphs. So I'm actually going to give you a zero-knowledge proof for any three colorable graph. So here's my graph, G. I know that it's three colorable. I have a coloring. I don't want to give you the coloring because I don't want you to know the coloring, but I have one. And here's my proof for you. The first thing I'm going to do is I'm going to put all the colors, but I'm going to put them in a safe. By the way, in a couple slides, I'm going to remove the safes and make them digital. Okay, but for now, let's start with being in the physical world a little bit, and then we're going to go back to the state of computers, okay, where there's no physical things. But for now, the first thing I'm going to do, I'm going to take my colors, put each one in a safe. What's a safe? The point is the verifier doesn't see what's in there. It's a locked box. The verifier gets no information. He gets n being the number of vertices, okay, in the graph. He gets n boxes that are opaque, and he can't open them because I have the key. I have the prover hold the key. So far, you didn't learn anything. You got, n kind of black boxes. Okay. Now the verifier will choose the verifier will choose a random edge. Okay, so two adjacent vertices, let's say I and J, in this graph, and he's going to ask for the edge. He's going to tell me, okay, I want you, essentially what he's telling me is I want you to open safes I and J. So I'm not going to open all the safes because then he learned my coloring. I don't want to do that. But so he can choose one edge and randomly, that's the randomness for you. He's going to choose one random edge and ask me, please open safes I and J. And I'm going to open these safes. Now, before I go into soundness and so on, what did the verifier learn? He learned only two colors. He did not learn all my color. He just learned two. Okay, and sorry, what does the verifier checks? The verifier checks that they're different because any two adjacent colors need to be different. He checks that they're different and that they're legal, namely they're, what's in there is either color 1, color 2, or color 3. Okay, so, okay. Now, before I go to soundness, what did the verifier learn? He got n boxes that are black. He can't see anything. And then I opened for him 2. I gave him the keys to 2, so he learned 2 colors. It's still information. So here's how I make it zero knowledge. Before I put my colors in the safe, I'm going to randomly permute the colors. What do I mean by randomly permute? I'm going to change my, let's say, color 1 to random color, I don't know, 2, color 2, I don't know, to random color 3, and then color 3 will be 1. Okay, I'm going to kind of just make them, I'm going to randomly permute. If I do this, if I first randomly permute the colors, now what did he learn? What did the verifier get at the end? And black boxes that give him no information. And then he opened them, but what did he see when he opened? He saw 2 random colors, 2 random distinct colors, because they have to be different. So, okay, so the verifier now can, of course he didn't learn anything because I can simulate it. Let me tell you, the graph is 3 colorable. Let me tell you why. N safes, black, a random vertex, and my 2 edges are random, 2 random distinct colors. And I generated a transcript. I don't even know that it's 3 colorable. I don't have a coloring. The point is, this doesn't give any information because what he gets at the end is just 2 random distinct colors. It has nothing to do with the actual legal coloring. No matter what the actual proof is, the actual legal coloring is, what the verifier is gonna get is 2 random distinct colors. Now, let me tell you, this is not a very sound protocol. You should not be happy, or proof. This is not a very sound proof. You should not be happy with it. Why? Because maybe the graph is not 3 colorable, but actually I can make it look almost 3 colorable. Maybe as long as you don't open safe N, let's say the last safe, it looks fine. So the soundness is really bad. Actually, I can cheat with probability, maybe. I mean, depends on the graph, but it may be that, okay, I know that what's in there is not a legal coloring. And because if the statement is false, so if G is not 3 colorable, then what the prover put in there is not a 3 coloring because such does not exist, which means there's some edge that he cannot open. But maybe all the other edges he can open. Or there's one edge that he cannot open in a satisfying way, that's 2 distinct legal colors. But maybe all the rest of the edges he can open, which means that he may be able to, he may be able to cheat with pretty high probability. With probability 1 minus 1 over the number of edges. But it's okay. Repeat it many times. As we said, we can repeat. For example, if you repeat it e times, e meaning the number of edges, then already the sounds will be 1 minus 1 over the number of edges to the power of number of edges, which is 1 over e. If you repeat it another 100 times, 1 over e meaning the small e. So anyway, if you repeat it, number of edges times 1,000, you'll get a very small probability. So again, just by just repeating it many times, you can get this probability done.
Let's see, there are a couple of questions I'm saving for the end. So if I don't get to your question, there were a couple that I think are better for the end. But let's see, Vivian, Han, did you get your question answered? Or do you want to ask that?
I think so. You said you randomly permute the coloring first. You do that for every single query, right?
Perfect. Okay, that was my next sentence. Great, Vivian. So I said we repeat it. Every time I repeat, I'm going to re-randomize. So I permuted my coloring. I gave you safes. You asked to open one. Well, two of the safes. So one random edge. Good. Now you say, let's do it again. Okay. I again randomly permute colors. I give you n safes. I open one edge. You want to do it again? Again, I randomly permute the colors. It's important to always randomly permute because at the end, the verifier sees many such executions. And what I want to argue is what he sees at the end is for each of these many executions, random distinct colors, again random distinct colors, again random distinct colors, again random distinct colors, which means he didn't learn anything. Or I can simulate that on my own without learning anything. So yes, Vivian, what you said is precisely right. Any other questions?
Yeah, I think there's a follow-up question. KG, do you want to ask your question?
Yeah, so how does the verifier know that like the colors were actually randomly permuted and not just like
he doesn't know.
Vague.
The verifier doesn't. Okay, that's a very good question. The verifier doesn't know that the colors were permuted, and he doesn't care because permuting the colors is not for soundness. It's only for zero knowledge. So if the prover doesn't want to reveal his witness or his colors, he better permute them. If the prover wants his proof to be zero knowledge, he should permute the colors. But if he permutes or doesn't permute, that doesn't harm soundness. The verifier, he just cares about soundness. He doesn't care, he's not like, I don't want to learn. That's not his concern. The prover, he's concerned with zero knowledge. He wants to say, I don't want to reveal my secret. I don't want to reveal my proof. So I care about zero knowledge. The verifier, he just cares that the statement is true. If the prover doesn't permute, that's fine. It just won't be zero knowledge. So the verifier does not verify that the colors are randomly permuted. And indeed, as you said, I don't think he can verify that.
Thank you, that makes sense.
Great questions. Yes.
Okay, so yeah, I just wanted to make sure you were aware of the time. It's 1:15 now. My suggestion is that we leave a little time, maybe go on for 5 minutes, a little bit more, and then leave some time for just some general questions. Does that work? Or
yes.
Okay.
So you want me to end in 5 minutes? Sure. So in that case, here's what we're going to do. I just want to say one thing. So far, we talked about digital safes. There's actually a way of implementing digital safes, and that's using what we call a commitment scheme. I don't want to define what a commitment scheme is, but there's something very interesting there, which involves some magic. But what I do want to say is that to construct this commitment scheme, and that's where the the crypto comes in some sense. That's kind of the bread and butter of cryptography. To construct these commitment schemes or to implement the safes, we need a cryptographic primitive that is called one-way functions, okay? And one-way functions, and actually in the first theorem that I flashed about zero knowledge, I didn't say it, but we know that we have a zero knowledge proof assuming one-way functions. I kind of skipped over it because I assume that none of you know what one-way functions are, but actually we have zero knowledge proofs assuming one-way functions exist. And so what are these one-way functions? I don't want to say too much, but essentially these are functions that are easy to compute, but hard to invert. Okay, so it's easy to compute them. Think of like multiplying two very, very large numbers. Multiplying is pretty easy. We can do it. But factoring turns out to be much, much harder. And we believe that it's hard to factor really large numbers, like 100, 200-digit numbers are very hard to factor. Okay, so that's just an example. And these are what's needed to construct these to implement these digital safes. The way we implement these digital safes, and I just want to point out this theorem that we use, not because I want to show you how to use it to get the safe, that's actually not important, I want to skip that. But because this theorem, I think, is the bread and butter, the father of all cryptography, and that's what allows you to get magic. And essentially, okay, so this theorem, what it says, if you have a one-way function, which we believe we have, but we don't have a proof, like the example of factoring, okay, or multiplying two large numbers. So here the theorem says that any such one-way function has some predicate that is very, very hard. So in other words, when I said it's hard to invert, maybe inverting the first bit. So f takes as input, let's say, n bits or n01010, to n bits, let's say. Now it's hard to find the inverse, but maybe the first bit or the first digit is easy. Maybe the second bit, maybe the second digit is easy. But all of them together is hard. So it's not clear that there's one digit that's hard. But the theorem, the Goldach-Levin theorem, says there is, maybe not a digit, but a predicate. So there's one function of the input, one bit of the input, which is p, that's what's denoted p. If a function is one way, given f of x, there's one bit in x that's really, really hard. It looks random. Okay, so given f of x, not only you cannot compute the entire x, there's one bit of x that just looks random. Now, this theorem is mind-blowing. The reason it's mind-blowing is essentially what it says, that using this cryptography, using one-way functions, essentially what did we do here? It's like I can pretend that I generated a random bit out of thin air. So here I have, let's say, x is, let's say, n random bits. Okay, think of f as a permutation for simplicity. Okay, so I took a permutation, I took n random bits. All I had is n random bits. But now when I concatenated with this hardcore predicate, with this predicate, all of a sudden it looks like I have n plus 1 random bits. I just generated randomness out of thin air. And that's kind of what allows us to implement the digital safes. And that's what allows us to do cryptography in general. That's what enables encryption schemes and everything else. Okay, so that's kind of what we did. We talked about zero knowledge. We constructed zero knowledge proofs for all of for 3 colorability, which is NP complete. So using that, you can generate zero knowledge proof for everything. Well, we didn't really construct digital safes, but we showed you essentially the way to do it is kind of to generate randomness out of thin air using the Goldach-Levin theorem, which is kind of really the magic of cryptography. And then I want to end in 2 minutes just by saying this is the beginning of the idea of proofs. Since then, proofs have evolved in unbelievable ways. Okay, and in particular, what was shown is actually this idea of moving to interactive proofs is so interesting, way beyond the idea of zero knowledge. So even if you don't care about zero knowledge at all, you don't care about knowledge. Turns out that classical proofs tend to be very, very long. They're not efficient. So for many statements, if you want to prove it, I just wrote there garbage, I don't know, but the point is it's very, very long. Oh. And it turns out that interactive proofs can be much more efficient, much more succinct. So just as an example, consider a chess game. Suppose I want to prove to you that in this configuration, the black player has a winning strategy. How would I give you a classical proof? I need to prove, the only way I know how to do it is to say, for any move of the white, there's a move of the black. So that for any move of the white, there's a move of the black. Blah, blah, blah. It's going to be a huge tree, like exponential size. Turns out that with an interactive proof, it's very short, and verification is very efficient. So that's pretty amazing. Moreover, let me tell you one more thing. After interactive proofs were considered, there was another model that was considered of two-prover interactive proofs. So now verifier is not only talking with one prover, he's talking with two provers that cannot interact with each other. So there's one prover in one room, the other prover in another room, and he tries to, he interacts with them. Turns out that here in this model, proofs are much more efficient. You can take any classical proof and make it exponentially shorter. So all these kind of, wow, that was, and this led, okay, I don't have time to say it, but it led to this unbelievable notion of what's called a probabilistically checkable proof. And with this, I want to end. So here's the notion. When I heard about it, I couldn't sleep at night. It's just mind blowing. So here it is. I can take any proof that you give me, and I can convert it. I can make it a little longer, not too much longer. Okay, a little bit longer, and such that to verify it, instead of reading, it's very tiring, one line, you need to read 3 bits of the proof. You choose 3 random locations in the proof to read, and you're convinced that the theorem is correct with probability at least 1/8. You want more than that? Read more, repeat. So now forget about reading all the, you need to read 3 locations. So this is kind of, so let me just wrap up with this. So what was, there was a classical proofs considered for thousands of years. In 85, all of a sudden zero knowledge proofs were considered. We learned every language, every proof can be converted to zero knowledge. Then multi-prover proofs were considered, PCP or probabilistic checkable proofs were considered. There's more since, interactive oracle proofs. So this kind of, proofs have evolved. And I want to say this is what's really nice about this is not only beautiful theory or math goes into it, but it's also applied. People use it now in a lot of blockchain technologies and elsewhere as well. So this is a very active and nice area of research. Okay, so I'll end here. Thank you so much. I liked your questions and I'm here to take more.
Okay, thank you so much, Yael. That was awesome. I think we have time. Why don't I take one question? Let's see. I think Chris Gu, do you want to just ask your question?
Absolutely, that would be awesome. Thanks so much, Professor. So I'm wondering, we've talked a lot about interactive proofs, and I find that super fascinating. But here's my question: are there any principles, theorems, postulates? Forgive me, I'm not very familiar with the jargon of this stuff here. But are there any of those theorems or principles that can never be proven besides using zero knowledge interactive proofs, or even proofs, or even theorems that can't even be proven through those means? For example, Fermat's last theorem is a principle that people have known for centuries, and there's so many people have tried to prove that it's almost like, is this impossible to prove? Only until 20-30 years ago, Andrew Weil spent an incredible amount of time to classically prove that theorem.
Right. So, okay, that's a very good question. So let me tell you, any interactive proof can be converted into a classical proof, but the classical proof will be much longer in general. So in general, if you take an interactive proof, let's say the number of symbols sent is S, the classical proof can be as big as 2 to the S. So theoretically, the answer is no, you can't prove more because anything can be converted. But practically, can anybody read 2 to the 1,000 number of bits, which is more than, I don't know, the atoms in the universe? Probably no. So, there's a question of practicality at the end. So theoretically, you can convert. Practically, no. Because interactive proofs are much more powerful. So you can do more practically with them than you could otherwise.
Mm-hmm. So, as you said, right? It could take 2 to the whatever, right? Which of course is an incredible amount of time. So theoretically, if we had an infinite amount of time, it could be, but because we're humans and we don't, therefore,
Exactly.
okay, got it.
Okay, I think we could go on for a long time, but we are running low on time. I did want to, before we wrap up, invite up Michael Flavity and Avi Chowdhury to make a little presentation. So do the two of you want to?
Yeah, so hi, Dr. Kalai. Let me just start off by saying what an honor it is to have you share your knowledge about the magic of cryptography through proofs, nonetheless. More specifically, I found myself to be quite fascinated by how you explain the concept of zero knowledge proofs and how they can be turned into colored graphs. And I can clearly understand how the concept of proofs can be shown in prover and the verifier when you talked about digital safes. And in class, we also talked about cryptography and encryption, and your explanation of one-way functions and how it is hard to invert back to it made me realize the importance of cryptography when it comes to security and really the magic and the artistic element again. So thank you again for your presentation.
Thank you.
Yeah, and I'd just like to reiterate, thank you so much, Dr. Kalai, for presenting these very important and applicable proofs to my peers and I. And I've always loved cryptography, and this talk has only reinforced that notion. And so on behalf of BWSI, I'd like to present you with a virtual Beaverworks t-shirt as a token of our appreciation. Yeah.
I love it. Thank you. And guys, I wanted to thank you. You guys were a great, great crowd. You know, giving a good talk is contingent on having a good crowd. So you had really, really great questions. I really enjoyed talking to you. It's pretty incredible that, you know, in your stage of life, you get an opportunity to kind of learn these things. I'm jealous. I wish I had that opportunity like you do. But thank you so much. Thanks for your listening and for your questions.
Yeah, thank you. Thank you so much for being here. And maybe just one very quick but parting question is, can you tell everyone a little bit about what an application of all this, you know,
one application
might be?
Yeah. So one place where it comes up, that's a recent application, is in applications like Bitcoin, even though it's not used in Bitcoin. So let me say a little bit about where it's used by other cryptocurrencies. But for example, today there's this cryptocurrencies. What is a cryptocurrency? There's no money involved, right? So think of it, there's kind of a ledger in the sky. It's in databases, but people, I tell you, look, I got a coin from, so say I want to, let's say, give a coin to Chris. I tell Chris, look, Avi gave me a coin, which I'm now going to give to you. But how does he know that the coin Avi gave me, I didn't spend already? And how does he know that the coin that Avi gave me is illegal? Maybe Avi's already spent that coin. So the way cryptocurrency works, every time you spend a coin, you write the transaction. The transaction is written in some public, it's called a public ledger. Think of it as it's like a big book that's all the transactions are written in order. Okay, so when Avi got a coin, she spent it, she gave it to Michael, and then Michael gave it to Chris, and every time when I want to pay, I use a coin that I got from someone. Now, when I give Chris my coin, he can't just take it and give me my good, whatever I bought, because how does he know it's legal? So now what does Chris needs to do? He needs to go verify that the coin I got, and then I did double spend, and go all the way to the origin of the coin. That's way too long, especially if the more and more people use these cryptocurrencies, it's not applicable. So the way new companies do it is they add a little proof, you know, that, oh, this coin was not double spent, it's legal. So it's not so much uses the zero, also they use zero knowledge, by the way, because they want to hide where it came from, but that's example where they use kind of these succinct proofs are very important. And there is no classical proof of doing that. So you need the succinctness. That's very, very important for these type of proofs. So that's an example where succinctness is used, and also they use the zero knowledge aspect of it to hide identities. So that's one application.
Okay, thank you so much. Let's see, Lisa, do you want to?
Yep. So thank you so much.
Yeah. Yeah. Why don't we all on clap and yeah, I mean, on mute and a round of applause. Thank you.
Thank you very much, guys. Good luck with everything. And okay.
Okay, Lisa, to you.
Okay.
Are you supposed to leave?
Please stay.
I'm still confused about the soundness, like the soundness value that she was talking about.
Oh, I responded to you in chat, but like from what I understand, it's more like what is the chance of the prover like lying and actually convincing the verifier that what they're saying is true, even though it's not actually true? Like, what's the probability that the prover can scam the verifier?
I think trust is a whole different question, right, Bob?
But I still don't get why the prover would lie, though. Like,
no, like, cause like, let's say you're trying to prove something that you don't know if it's true or not. So like, the probability that you
that I'm incorrect or something.
Yeah, like the probability that you think it's true, and from your data, it looks like it's true. What is the probability that it's actually false?
So that's the soundness. Like
Yeah.
The probability. Okay, that makes sense.
Right. Hey, Lisa. My apologies. I accidentally give the impression that the meeting was over, but we do have the
Yeah,
students.
I'll just talk on Monday.
Okay. But
Then we
you know, sorry.
That's
Right.
okay. So have a good weekend, everybody. See you guys Monday.